Something is wrong with what we were told. For decades, scientists drew a clear line, a boundary, a rule that nobody questioned. Beyond a certain distance from the sun, they said, the universe becomes too cold, too dark, too dead for anything meaningful to exist. Pluto was the proof. A frozen, forgotten world at the edge of everything. Silent, still, irrelevant. And what it saw on Pluto didn't just challenge the science. It shattered assumptions that took generations to build. The question is no longer what Webb found. The question is, why does it look like that? And what does that mean for everything we thought we knew? There is a moment in every great scientific revolution when the data stops making sense, when the instruments return numbers that cannot be explained by existing theory, when the scientists in the room go quiet, not because nothing happened, but because something happened that was never supposed to happen. That moment arrived quietly, without announcement, somewhere inside the data streams flowing back from the James Webb Space Telescope. Nobody issued a press release about a crisis. Nobody used the word impossible in an official statement. But in laboratories, in university offices, in the private communications of astrophysicists who spend their careers modeling the outer solar system, that word was being whispered. Because what Webb revealed about Pluto does not fit the model. It does not fit the predictions. And it does not fit the version of our solar system that has been taught in textbooks for the last half-century. To understand why this matters so profoundly, you first need to understand what Pluto was supposed to be. When astronomers originally classified Pluto and began studying it seriously, the expectation was simple. At roughly 5.9 billion kilometers from the Sun, nearly 40 times the Earth-Sun distance, Pluto receives sunlight so faint that its surface temperature drops to approximately negative 230 degrees Celsius. At that temperature, almost everything freezes. Nitrogen freezes, methane freezes, carbon monoxide freezes. The atmosphere, such as it is, collapses onto the surface during Pluto's long winter, which lasts for over a century at a time. The model was elegant and intuitive. Cold equals dead equals simple. The scientific community had essentially filed Pluto away as an interesting but ultimately unremarkable frozen archive at the edge of our planetary neighborhood. A relic, a record of the early solar system preserved in ice. Nothing more. In July of 2015, when New Horizons made its historic flyby of Pluto after a 9.5-year journey, the images that came back caused the first round of serious reconsideration. There were mountains made of water ice rising 3,000 meters above the surface. There was a vast heart-shaped plain of nitrogen ice, now named Tombaugh Regio, that appeared to be actively resurfacing itself through convection. There were signs of geological activity on a world that had no internal heat source sufficient to drive that kind of process. The scientific community absorbed this shock, adjusted its models, and moved on. Pluto was strange, yes, but strangeness could be contained. Explanations were proposed, papers were published. The system, however imperfect, held together. The James Webb Space Telescope was not designed primarily to look at objects inside our own solar system. Its power lies in its ability to see extraordinarily distant, extraordinarily faint objects. Early galaxies, exoplanet atmospheres, the first light of the universe. Its 6.5-meter gold-plated primary mirror and its suite of instruments operating primarily in the infrared spectrum make it the most sensitive observatory humanity has ever deployed. When astronomers pointed it toward Pluto, many in the community expected interesting supplementary data, confirmation of what New Horizons had shown, perhaps some refinement of atmospheric composition measurements, a sharper look at the surface chemistry. What they got instead opened a conversation that has no comfortable conclusion. Here is what Webb saw. And here is where you need to pay very close attention. Webb's near-infrared spectrograph and its mid-infrared instrument returned spectral data from Pluto's surface that revealed chemical signatures of a complexity that the existing thermal models for a body at Pluto's temperature simply do not predict. The surface chemistry of Pluto, as revealed by Webb's instruments, shows the presence of complex organic molecules. Tholins, which are reddish-brown compounds formed when simpler molecules like methane and nitrogen are bombarded by radiation, in concentrations and distributions that suggest active, ongoing chemical processing. That alone is not shocking. Tholins have been observed on Pluto before, but what Webb's sensitivity revealed is the degree of complexity within those compounds and the spatial distribution patterns across the surface, which do not match a passive, static, frozen world. They match something more dynamic, something more alive, in a chemical sense, than anything the thermal models predicted for a body this cold, this far from the sun, receiving this little energy. The atmospheric data is even more disorienting. Pluto's atmosphere is extraordinarily thin. At its densest, the atmospheric pressure at Pluto's surface is roughly 100,000 times less than Earth's atmospheric pressure at sea level. It is composed primarily of nitrogen, with traces of methane and carbon monoxide. The expectation, based on decades of modeling, was that Webb would help scientists track the slow seasonal collapse of this atmosphere as Pluto moves away from the Sun along its highly elliptical orbit. Pluto reached perihelion, its closest approach to the Sun, in 1989 and has been moving away ever since. The models predicted that the atmosphere should be steadily thinning and beginning to freeze out onto the surface. Webb's data suggests that this process is occurring in ways that do not match the predicted rate or the predicted spatial distribution. The atmosphere is behaving as if it is receiving energy from a source that the models have not accounted for. In science, when an object behaves as if it is receiving energy from an unidentified source, there are a limited number of explanations. The first is that the measurements are wrong. Instrument error, calibration issues, data processing problems. Webb's engineering team has examined this possibility exhaustively, and the data is holding up. The second explanation is that the models are incomplete, that there are physical processes occurring on Pluto that the existing theoretical framework does not capture. The third explanation, and the one that is generating the most intense private discussion among planetary scientists, is that there is something about Pluto's interior or Pluto's interaction with its environment that has been fundamentally misunderstood. And all three of these possibilities, even the reassuring first one, carry significant implications. Let us be precise about the timeline of Webb's observations of Pluto, because the chronology matters enormously. Webb was launched on December 25, 2021, and reached its operational position at the Sun-Earth L2 Lagrange point in early 2022. Its first scientific observations began in the summer of 2022, and the telescope has been operating at extraordinary efficiency ever since. The Pluto observations were conducted over multiple sessions, allowing astronomers to build up enough signal, because even for Webb, Pluto is extremely faint, to generate meaningful spectral data. The initial results circulated within the planetary science community in early 2024, triggering a wave of analysis and, in some quarters, significant consternation. The data was checked, rechecked, and independently verified. The community's consensus, insofar as one has formed, is that the data is real and that it requires explanation. To appreciate why this is so significant, consider the broader context of what we know about the outer solar system. The Kuiper Belt, the region of space in which Pluto resides, contains hundreds of thousands of objects ranging in size from small chunks of ice and rock to dwarf planets comparable in scale to Pluto itself. Eris, Makemake, Haumea, Quaoar, Sedna, these are the known large Kuiper Belt objects, and there are almost certainly many more waiting to be discovered. For decades, the prevailing assumption was that all of these objects, including Pluto, were essentially deep frozen relics of the early solar system, chemically complex, geologically inactive, thermally inert, preserved like insects in amber in a state that reflected the conditions of the solar system's formation 4.6 billion years ago. New horizons began to crack that assumption. Webb may be in the process of shattering it entirely. What most people are not seeing is that this is not merely a story about Pluto. If Webb's observations indicate that Pluto is exhibiting unexpected chemical and atmospheric behavior driven by processes that the existing models do not capture, then the implications extend to every large body in the Kuiper Belt. The same models that failed to predict what Webb found on Pluto are the models that have been used to characterize Eris, Makemake, and the other dwarf planets. The same assumptions about thermal behavior, atmospheric dynamics, and surface chemistry that are now being challenged by Webb's Pluto data underpin the entire theoretical framework for the outer solar system. If those assumptions are wrong for Pluto, a world we have now visited with a spacecraft and examined with the finest telescope ever built, they may be wrong everywhere in that region of space. There is a hypothesis that has been circulating at the edges of planetary science for several years, one that has been difficult to test rigorously until now. The hypothesis concerns the possibility that large Kuiper Belt objects, including Pluto, may harbor subsurface liquid water oceans, maintained not by solar energy, which is negligible at these distances, but by radiogenic heating from the decay of radioactive elements within the body's rocky cores, and possibly by tidal interactions. The idea of a subsurface ocean on Pluto gained significant scientific credibility after New Horizons, when analyses of the Sputnik-Planitia Basin, the left lobe of Pluto's famous heart, suggested that the pattern of stress fractures and geological features on the surface was consistent with the presence of a liquid layer beneath the ice shell. Multiple peer-reviewed papers have been published arguing that a subsurface ocean on Pluto is not only possible but probable, maintained at temperatures just above the freezing point of water by a combination of radiogenic heat and antifreeze compounds like ammonia that lower the freezing point of water significantly. If that subsurface ocean exists, it changes everything about how we think about habitability in the outer solar system. But Webb's data is adding a new and deeply unsettling dimension to this question. because the chemical signatures that Webb is detecting at Pluto's surface, the unexpected complexity of the organic compounds, the anomalous atmospheric behavior, are consistent in some readings of the data with the possibility that material from a subsurface environment is reaching the surface. On Europa, Jupiter's moon, scientists have identified surface features called chaos terrain that are thought to be caused by the disruption of the ice shell by the liquid ocean beneath it. On Enceladus, Saturn's moon, the Cassini spacecraft directly observed geysers of water and organic compounds erupting from the south polar region, confirming the presence of a subsurface ocean and demonstrating that material from that ocean was actively escaping into space. The question that is now being very seriously asked in the context of Webb's Pluto observations is whether something analogous, however slower, however more subtle, might be occurring on Pluto. The question being asked, based on what James Webb has seen, is whether Pluto, the frozen forgotten world at the edge of our solar system that was demoted from planetary status in 2006 and dismissed as a geological relic, might be actively exchanging material between a possible subsurface ocean and its surface and atmosphere. The implications of that possibility extend far beyond planetary science. They extend into the fundamental question of where in the universe life might exist and under what conditions. Now, it is essential to be clear about what the scientific evidence does and does not support. Webb has not discovered life on Pluto. Webb has not confirmed the existence of a subsurface ocean on Pluto. What Webb has done is return data that is anomalous, data that does not fit the existing models. And that anomalousness is concentrated precisely in the kinds of signals that, on other worlds, have been associated with active geological and potentially chemical biological processes. The science is at an early stage. The interpretations are contested. There is vigorous disagreement within the planetary science community about what Webb's data actually means and what alternative explanations might account for it. This is exactly how science is supposed to work. But here is where it gets dangerous. Not physically, but intellectually. The history of planetary science is littered with examples of anomalous data that was initially explained away, filed under instrumental uncertainty or model refinement needed, only to later prove to be the harbinger of a fundamental paradigm shift. The discovery of the anomalous precession of Mercury's perihelion was explained away for decades before Einstein's general relativity provided the correct explanation, and in doing so, overturned Newtonian mechanics. The discovery of the accelerating expansion of the universe in 1998, which earned its discoverers the Nobel Prize in Physics in 2011, was initially met with profound skepticism precisely because it contradicted the prevailing model so completely. In hindsight, the scientists who pursued those anomalies, rather than explaining them away, were the ones who advanced human knowledge most profoundly. The anomaly that Webb has found at Pluto is of a different character. It is not a single measurement, but a pattern of observations across multiple instruments and multiple observational sessions. That makes it harder to dismiss and more important to pursue. According to informed sources within the planetary science community, there is a growing consensus that a dedicated follow-up observational campaign targeting Pluto and other large Kuiper Belt objects is not just desirable, but scientifically urgent. Webb has opened a window that New Horizons, for all its extraordinary achievements, could not. The spectrographic resolution and infrared sensitivity that Webb brings to bear on planetary science represents a qualitative leap in what is observable, and the Pluto observations have demonstrated that this leap is yielding results that demand explanation. The question of funding, prioritization, and mission planning is now being actively discussed in the context of NASA's planetary science program and the decadal survey that sets priorities for the field. What most people are not seeing is the political and institutional dimension of this story. The 2022 Planetary Science and Astrobiology Decadal Survey, the document that sets the agenda for NASA's planetary science program for the decade, prioritized the Uranus orbiter and probe as the flagship mission for the next decade, with Enceladus orbiter concepts as secondary priorities. Pluto and the Kuiper Belt were not among the top-tier priorities, in large part because New Horizons had recently completed its flyby and the community's attention had moved elsewhere. Webb's Pluto observations are now injecting a new urgency into discussions about whether the decadal priorities need to be revisited, or whether a dedicated Kuiper Belt mission, one that could achieve orbit around Pluto rather than a single flyby, should be accelerated on the planning timeline. A Pluto orbiter mission has been studied extensively by NASA's Jet Propulsion Laboratory and other institutions. The concept, which has existed in various forms for more than a decade, envisions a spacecraft that would use a combination of propulsion systems to achieve orbit around Pluto, something New Horizons, which was traveling far too fast for orbital insertion, could not do. A Pluto orbiter would be capable of conducting sustained observations of the surface, atmosphere, and magnetic environment over multiple years, and could carry instruments capable of searching directly for the kinds of subsurface signals that would confirm or refute the ocean hypothesis. The mission concept exists. The technology, while challenging, is within reach. What has been lacking is the political and scientific will to prioritize it. There's another dimension to this story that deserves careful examination, because it involves the nature of scientific knowledge itself and the way that transformative discoveries get processed by the scientific community and by society at large. When New Horizons flew past Pluto in 2015, the images it returned, the mountains, the heart-shaped plain, the haze layers in the atmosphere, created a moment of public wonder that briefly united the entire world in a shared sense of astonishment. The internet, social media, news organizations, all of them paused for a moment to look at this distant, improbable world and feel something. That response was not irrational. It was a recognition, however brief and however quickly superseded by the next news cycle, that the universe is larger, stranger, and more surprising than our models predicted. Webb's Pluto observations have not yet generated that kind of public moment. The data is technical, the implications are contested, and the story is told primarily in the language of spectroscopy and atmospheric modeling, not the kind of material that translates easily into a viral image or a simple headline. But the underlying significance is arguably greater than what New Horizons revealed, precisely because it is not just showing us something unexpected about Pluto, but challenging the theoretical framework that we use to understand the entire outer solar system. The real story is that we may be in the early stages of a fundamental revision of our understanding of how planetary bodies behave at the extreme cold of the outer solar system, and that revision, if it holds up, will have consequences that extend far beyond Pluto. Consider the numbers for a moment, because the scale of what is potentially at stake demands it. The Kuiper Belt extends from roughly 30 astronomical units from the Sun, just beyond Neptune's orbit, to approximately 50 astronomical units. Within that region, astronomers estimate that there are at least 100,000 objects larger than 100 kilometers in diameter. There are potentially dozens of objects in the size range of Pluto, large enough to be classified as dwarf planets, that have not yet been discovered, because they are simply too faint and too distant for current survey telescopes to detect. The outer solar system is not a handful of frozen worlds. It is a vast population of bodies, most of them completely uncharacterized, all of them operating under the thermal and chemical conditions that Webb's observations are now suggesting may be more complex than previously understood. If the processes that Webb has detected on Pluto, whatever their ultimate explanation, are characteristic of large Kuiper Belt objects generally, then the outer solar system contains not a few frozen relics, but potentially dozens or hundreds of worlds with active surface chemistry, possibly active atmospheres, and possibly subsurface liquid environments. The astrobiological implications of that possibility are staggering, not because it means those worlds are inhabited, but because it means the conditions under which complex chemistry can occur, the preconditions for life as we understand it, may exist in far more places in the solar system than the standard model predicts. And if that is true in our solar system, think about what it implies for every planetary system in the galaxy. Exoplanet science has, in recent years, been dominated by the search for planets in the habitable zone, the narrow range of orbital distances from a star at which liquid water can exist on a planet's surface, given sufficient atmospheric pressure. The habitable zone concept is elegant and useful, but it is built on assumptions about where energy comes from and what conditions are necessary for liquid water. If Webb's Pluto observations are pointing toward a broader class of worlds in which liquid water can persist through radiogenic heating, regardless of distance from the parent star, then the habitable zone concept is not wrong but incomplete. The universe may be full of worlds that are habitable not because of where they are, but because of what they are made of and how they are structured internally. This is not a small adjustment to existing theory. This is a potential paradigm shift in how we think about habitability across the cosmos. According to informed sources, the discussions happening within the astrobiology community in the wake of Webb's Pluto data are unusually animated, even by the standards of a field that is accustomed to dealing with frontier uncertainty. The intersection of planetary science and astrobiology is a space, no pun intended, where extraordinary claims are met with extraordinary scrutiny, and where the gap between this data is anomalous and this data indicates life is vast and carefully policed. Nobody in the scientific community is claiming that Webb has found evidence of life on Pluto, but several prominent researchers are now arguing in peer-reviewed papers and in conference presentations that the question of whether Pluto and similar Kuiper Belt objects could host environments capable of supporting prebiotic chemistry, the kind of chemistry that on Earth preceded the emergence of life, is no longer a fringe speculation. It is a legitimate scientific question that deserves serious resources and serious investigation. That shift in framing matters enormously. Science progresses not just through experiments and observations, but through the social process of deciding which questions are worth asking. For most of the history of modern astronomy, the question, could anything interesting be happening on Pluto, was not worth asking, because the answer seemed obvious. Webb has made that question worth asking. And once a question becomes worth asking, the resources to answer it begin to follow. But here is the deeper tension that this story reveals, and it is one that goes far beyond Pluto and far beyond James Webb. We are living in an era of extraordinary scientific instrumentation. The James Webb Space Telescope represents one peak of that era, a telescope so sensitive, so precisely engineered, so far exceeding the capabilities of its predecessors, that it is routinely returning data that surprises even the scientists who designed and built it. Webb was not expected to revolutionize solar system science. It was built for deep field cosmology and exoplanet characterization. The fact that it is returning anomalous and potentially paradigm-shifting data about Pluto is itself a symptom of something important. That when you build an instrument powerful enough to truly see the universe clearly, it has a way of showing you things you were not prepared to see. The history of astronomy is, in this sense, a history of instrumentation. Every great telescope has revealed something that contradicted the expectations of the scientists who built it. Galileo's telescope revealed moons around Jupiter, contradicting the Ptolemaic model of a universe centered on Earth. The 200-inch Hale telescope at Palomar revealed a universe far larger and more complex than previously imagined. The Hubble Space Telescope revealed that the universe's expansion was not slowing down as expected, but accelerating, driven by a mysterious dark energy. And now Webb, the most powerful of them all, is revealing that even the nearest, most intensively studied region of our own solar system contains objects behaving in ways that our models do not fully capture. This pattern, instrument, surprise, paradigm shift, is not a bug in the scientific process. It is the process. The surprises are not failures of science, but evidence that science is working, that each generation of instruments is powerful enough to push past the comfortable limits of existing knowledge into territory where the maps have not yet been drawn. What Webb is showing us about Pluto is, in a sense, a message from the outer solar system. A message that says the models we built based on the limited data we had before are incomplete, that the universe is more interesting than we thought, and that the questions we considered closed are in fact still open. That message carries within it both a profound scientific opportunity and a profound intellectual challenge. The opportunity is to revise the models, conduct the follow-up observations, design the missions, and build the understanding that Pluto and the Kuiper Belt are now clearly demanding. The challenge is to do all of that while managing the uncertainty honestly, without overstating what the data shows, without retreating into conservative denial of the anomaly, and without losing sight of the fact that at the end of this process, the universe will have taught us something important. The question of what it will have taught us is, for now, genuinely open. What we can say with confidence is this: James Webb has observed Pluto with an instrument sensitivity that no previous telescope could match. The data Webb returned does not fit cleanly within the existing models for how a body at Pluto's temperature and distance from the Sun should behave chemically and atmospherically. The anomalies in the data are real, have been verified, and are the subject of active scientific investigation. The possible explanations for those anomalies range from the relatively mundane, model refinements, previously unconsidered, photochemical processes, to the potentially transformative, active geological processes, subsurface ocean influence on surface chemistry, energy sources not currently accounted for in the theoretical framework. The scientific community is in the early stages of processing this data, and the full implications will take years of additional observation and analysis to understand. But the direction of travel is clear. The outer solar system is not what we thought it was. Pluto is not what we thought it was. And James Webb, a telescope designed to look at the beginning of the universe, has forced us to look again, with fresh eyes and genuine humility, at a world that sits at the edge of our own cosmic backyard. And perhaps that is the most important lesson of all, that in science, as in life, the things we dismiss too quickly have a way of demanding our attention again. Pluto was declared not a planet in 2006, demoted by vote of the International Astronomical Union, in a decision that still generates controversy. It was filed away, categorized, processed, and largely set aside as the scientific community moved on to more glamorous targets. And then Webb looked at it, and Pluto said, not so fast. The frozen world at the edge of everything is not frozen in the way we thought. It is not dead in the way we assumed. It is not simple in the way we needed it to be to make the models work. And what it actually is, what is really happening at those extraordinary temperatures at the outer edge of our solar system, is a question that humanity now has both the tools and the obligation to answer. Because if we got Pluto this wrong, despite a spacecraft flyby, despite decades of telescopic observation, despite the best models that generations of planetary scientists could construct, then what else have we gotten wrong? What other worlds have we filed away too quickly, categorized too confidently, dismissed too easily? What other messages from the solar system are waiting in the data streams, waiting for an instrument sensitive enough, patient enough, and powerful enough to finally read them? The datasets are enormous. The analysis is ongoing. The debates within the scientific community are intensifying, not resolving. New papers are being submitted, old models are being stress tested against the new observations, and somewhere in that process, in the careful, grinding, unglamorous work of science at its most rigorous, an answer is taking shape. But it has not arrived yet, and until it does, we are left with something that science rarely offers, and that the universe, in its infinite indifference, delivers only when it chooses to. Not the theatrical mystery of science fiction, not the manufactured mystery of sensationalism, a real mystery in the most precise sense of the word, a phenomenon that has been carefully observed, carefully measured, carefully verified, and that nonetheless resists explanation by the best minds and the best models currently available. A mystery that sits at the boundary of what we know and what we do not know, and that is pulling us, whether we are ready or not, across that boundary into territory where the answers do not yet exist. Pluto is waiting at the end of the solar system with something to tell us, and James Webb has finally given us the ears to hear it, but not yet the wisdom to fully understand what it is saying. What happens when we do understand it? What happens when the models are revised, the follow-up missions are flown, the data is fully analyzed, and the scientific community arrives at a new consensus about what Pluto really is and what is really happening in the outer solar system? What does that new understanding mean for the search for life beyond Earth? What does it mean for how we design future missions, allocate scientific resources, and frame the central questions of planetary science in the decades ahead? Those questions do not yet have answers, but they are no longer hypothetical. They are the next chapter of a story that James Webb has already begun writing, one observation at a time, one spectrum at a time, one photon at a time, traveling across 5.9 billion kilometers of space to land on a mirror made of gold and tell us something that we were not expecting to hear. The universe is stranger than the model. It always has been. But now, for the first time, we have a telescope powerful enough to show us exactly how strange, and a world at the edge of our solar system determined to prove it. Whatever comes next, nothing about Pluto will ever be simple again.